Hello, my name is Raluca Dumitriu, and this presentation deals with electrospun fibrous coatings with antimicrobial and antioxidant properties. Development of engineered materials with a desired functionality and certain surface properties can be a challenging task. Antimicrobial or antioxidant effect of the designed materials can be achieved by incorporation of active or bioactive agents such as essential oils and vegetal extracts, vitamins, or naturally derived polysaccharides. In many cases, it's desirable not to change the bulk material, but only the surface properties in order to ensure a certain functionality. Therefore, an attractive option is to incorporate antimicrobial agents or antioxidants in the coatings to obtain the active materials desired. Coatings are able to provide protection, safety, to improve product quality by preserving its functionality and surface properties. A category of special interest in recent years are the fibrous coatings that can be obtained by electrospinning. Electrospinning is a versatile and low-cost technique known for its efficiency and productivity, having wide applicability in the field of polymers, offering high surface area to volume ratio, and enabling the production of continuous uniform fibers with diameters down to nanometer sizes. The electrospun fibers obtained can have many applications in industry as multifunctional membranes, nanocomposite, filtration systems, protective clothing coatings, or in the biomedical field as 3D scaffolds for tissue engineering, wound dressings, vascular grafts, and so on. The aim of the present study was the obtaining of new fibrous coatings by electrospinning as materials with certain surface properties and desired functionality, namely antimicrobial or antioxidant. In order to obtain the fibers, a classical horizontal experimental electrospinning setup was used as the one presented in figure. Therefore, the materials used for this study were polyepsilon caprolactone as starting polymer, well-known biodegradable polymer, bioresorbable, biocompatible with hydrolytic stability, non-toxic and commercially available. Polymer that can be a substitute material for non-degradable polymers, can be used in composites together with biopolymers. The active substances introduced in composition of the fibers were alpha-tocopherol and chitosan. Alpha-tocopherol, or vitamin E, is a fat-soluble phenolic compound found in plant tissues known for anti-inflammatory effect on skin and potent antioxidant ability, offering protection against UV radiation and decreasing lipid peroxidation. Chitosan is a naturally derived polysaccharide with hemostatic potential, hydrophilic character, known for antimicrobial activity. Therefore, solution prepared based on polyepsilon caprolactone and alpha-tocopherol on one side and polyepsilon caprolactone with chitosan on the other side were tested for electrospinning. By tuning the deposition parameters like applied voltage, flow rate, distance between collector and needle, combined with the solution properties like concentration, conductivity, viscosity, it's possible to obtain either continuous fibers by electrospinning or small droplets or microparticles by electrospraying process. In order to obtain uniform continuous fibers by electrospinning, the rheological behavior of the fiber-forming solution mixtures should be investigated in order to assess the influence of blend solution composition on the flow behavior and viscoelastic response in view of the electrospinning conditions. Therefore, the rheological behavior of the fiber-forming solutions was studied. The flow behavior investigation showed a generally shear thinning behavior for all the mixtures prepared, with viscosity values at low shear rates that are intermediate between those of the two main components. For the PCl alpha tocopherol system, Newtonian behavior of vitamin E on the entire shear rate range is observed, while PCl presented shear thinning behavior with Newtonian plateau up to a critical shear rate. In the case of PCl chitosan system, only PCl presented Newtonian behavior, while chitosan and all the mixtures PCl chitosan behaved as non-Newtonian fluids. These differences in behavior can be attributed to the different solvents that were used. For the PCl alpha tocopherol system, the solvent was dichloroethane, while for PCl chitosan, the common solvent was acetic acid. The shape of the shear stress, shear rate curves show clearly the Newtonian behavior of vitamin E in the first case and of PCl in the second case, with the shear stress increasing linearly with the shear rate, as compared with the non-linear pseudoplastic behavior for the other solution mixtures. Also, it's observed that shear stress values vary depending on the mixture's composition. The dynamic oscillatory measurements evidenced a viscous behavior for the main components of the mixtures prepared, namely PCl, vitamin E, and chitosan. Also, viscous behavior for the mixtures obtained from PCl and alpha tocopherol, while the mixtures of PCl with chitosan presented elastic behavior over a wide frequency range, with G' values almost independent of frequency. Therefore, the presence of chitosan in the mixtures imparts a higher elasticity to the solution through the enhanced entanglements, rendering it more suitable to form uniform fibers. The morphology of the fibrous coatings obtained were studied by scanning electron microscopy. The SEM micrographs evidenced a fiber mesh with homogeneous morphological aspect, but with less uniform fibers for the system based on PCl and alpha tocopherol. The fiber dimensions were in the microscale range with an average of 6 microns, and it was noticed narrower distribution of the fiber diameters at a higher tocopherol content. For the PCl chitosan mixtures, the coating had a homogeneous morphological aspect with more uniform fibers, with fiber dimensions in the nanoscale range. The average diameter of the fibers decreases with increasing chitosan content from 124 nanometers down to 80 nanometers in the case of pure chitosan. In correlation with the results of rheology study, the elastic behavior of the PCl chitosan mixtures prevents jet breaking and promotes the formation of more uniform fibers with significantly decreased diameters down to nanoscale. The wettability of the coatings was investigated by static contact angle measurements, static water contact angle measurements determined by Cecil drop method. The values of the contact angle obtained showed a low wettability due to the higher values, showing the hydrophobic character of the surface, and even super hydrophobic surface in the case of fibers with higher tocopherol content, the values of the water contact angle being above 130, even 140 degrees. For the PCl chitosan fiber meshes, the surface became hydrophilic by adding chitosan in composition. At 20% chitosan in composition, the water contact angle is already below 90 degrees. Therefore, fibrous coatings with tailored surface properties can be obtained, controlling the wettability through the influence of the hydrophilic or hydrophobic component in the solution mixture. The antioxidant activity of the coatings was tested also by DPPH and ABTS tests, and the radical scavenging activity was calculated, measuring the inhibition of the free radicals. The results obtained showed an enhanced antioxidant effect of the electrospun fibers with a higher alpha-tocopherol content. The effect on microbial growth of the fibrous coatings obtained was tested by respirometry. A preliminary test was performed of the inhibitory effect of meshes on the microbial growth on cheese samples. In general, the deleterious effect of oxygen is delayed by application of an antioxidant or anti-browning agent. In the case of electrospun fibers, the high surface area provide a facile accessibility of the oxygen towards the active component incorporated in the fiber, in our case for alpha-tocopherol and respectively for chitosan. The results obtained showed that PCL fibers containing alpha-tocopherol provided a more efficient protection against oxidative stress in the first 48 hours. But generally, all the fiber meshes tested inhibited microorganism growth as measured by the oxygen consumption. In conclusion, electrospun fibers with controlled surface properties and desired functionality were obtained from PCL tocopherol and PCL chitosan. The rheological behavior of the fiber-forming solution mixtures was influenced by the hydrophilic or hydrophobic nature of the component added to PCL. The mixtures of PCL with chitosan showing predominantly elastic behavior enable the formation of more uniform fibers with diameters down to nanoscale dimensions, while the PCL alpha-tocopherol system had microscale dimensions in the diameter of the fibers. Fibrous coatings with a controlled wettability can be obtained, with a superhydrophobic effect induced by alpha-tocopherol presence and the hydrophilic surface by adding chitosan. The DPPH and ABTS tests showed that alpha-tocopherol preserved its antioxidant efficiency within the electrospun fibers, providing enhanced antioxidant effect for the coatings with a higher vitamin E content. The inhibitory effect of meshes on the microbial growth was observed by respirometry. Thank you for your attention and for the opportunity to participate in this conference.